Welcome back, AP Statistics. This is the second part of Chapter 5. We're going to be talking about the normal model, and actually we'll be talking about normal models, plural. There are many different variations on the normal model, and that's what we'll be talking about in this lesson. So, the most famous classification of bell-shaped curve, there's more than one, we'll be talking about several this year, used to approximate the distribution of data is called a normal model or normal distribution. All right, both terms are used to describe this curve. I will use them interchangeably. And that is written in this interesting little notation right here. The n means we are using a normal model. It's a bell-shaped curve kind of like this. This is mu, refers to the population mean, and sigma refers to the population standard deviation. So this normal model has a center and spread. Mu and sigma are the mean and standard deviation, respectively, for this normal model. They are called parameters because they describe a population, right? That goes back all the way to Chapter 1. Parameters describe a population, all right? Population is all possible subjects that we could study, as opposed to statistics that describe a sample, that is a subset of all possible subjects, okay? So we use parameters to describe this curve that we are fitting to a set of data. As we've noted, parameters are almost always represented by Greek letters. This is a Greek letter mu, Greek letter sigma. Whereas statistics for samples are almost always represented by Roman letters, like X with a little bar and S. Let's look at the standard normal model, and let's contrast that with other normal models. N01 is called the standard normal model. That's the standard normal distribution. Again, I'll use that interchangeably. Since it's the normal model but standardized, all right? Remember from the last lesson, when you standardize a set of data, you are setting the mean to be equal to 0 and a standard deviation to be equal to 1. Okay, that is what standardizing does. There are, of course, other normal models, all right? You can fit a normal distribution curve to data that are not centered at 0, of course. For example, a normal model mean of 20, standard deviation of 3 would be the normal distribution centered at 20, having a spread in the form of standard deviation of 3, okay? So, the nearly normal assumption is what we're going to be talking about next, all right? We're not going to be assuming normality, all right? That gets a little bit hairy. We're going to talk about the nearly normal assumption. That is a phrase our textbook uses to describe an assumption we need to make in order to use a normal model. So in order to use the normal distribution, in order to use a normal model, we need to make sure the data are distributed in the neat bell shape. Of course, no data looks quite that nice. Now, why is Jurassic Park here? Well, in the book Jurassic Park, there's a part where I cannot remember his name, but one of the individuals who is investigating Jurassic Park, is this safe? Is this legit? Encounters researchers and looks at some of the statistics about the critters in the park. And he notices that the bell curves are a little too nice and neat. And that actually sends alarm bells going off, okay? For him, he says, it's not that they're doing a really good job managing the dinos. It's actually that these statistics are forged, all right? And it turns out that he's exactly right. because, as you know from the movies, if you've seen them, same thing happens in the book. The dinos go crazy, all right? They cannot be contained, and they wreak havoc, okay? So no data looks quite that nice. If you see data that look a little too clean, a little too nice, well, you could have some raging dinosaurs on your hands. However, if a set of data meets the nearly normal assumption, namely the data's distribution is unimodal and symmetric, which can be observed in a dot plot or a histogram, as we've seen, the normal model can be used to analyze the data. We don't want to use a box plot. Box plots are awesome, all right? Box plots cannot show the desired bell shape. Now, I can show you a box plot that is probably bell-shaped, but it's a little risky, all right? It is a little bit risky. Sometimes a box plot may reveal may look like it reveals a bell-shaped distribution when it may be bimodal or multimodal or something like that. And you got to be careful with box plots, all right? So we're going to be looking at histograms to help us make sure we can fit a normal model to describe a set of data. Which brings us to what is called the empirical rule, what old school statisticians call the empirical rule. This textbook refers to it as the 68, 95, 99.7 rule. Why all these numbers? Well, this is actually, I would argue, a better name than the empirical rule. Just the word empirical is not true, in my opinion, to what's going on. Empirical means found through the process of research. Well, we can model this mathematically and use calculus, all right? So it's a little bit confusing why we call it empirical, but 68, 95, 99.7, that actually describes what's going on mathematically a lot better. So this rule, whatever you choose to call it, for data that nearly fits the normal model, the distribution of data is predictable, okay? That is a huge phrase, all right? If data are said to be predictable, that means that we can bring in more and more and more data values, and if we think the distribution of data is going to be predictable, the bigger the sample, the better it's going to fit this nice curve here. We're dealing with a variable that is knowable, that is understandable, that is predictable in nature. And that's really neat, okay? So if our data fit a nearly normal model, and we have evidence that, say we were to add more and more and more data values, it would just better and better assume this nice bell shape right here. About 68% of the data can be found within one standard deviation of the mean. Now, what does that mean? Within one standard deviation. Well, here's the mean. A z-score of 0 refers to the mean. The mean for standardized data has a z-score of 0. Okay? You can also see it's labeled the mean down here. Just wanted to reinforce that concept. Okay? So, one standard deviation below, mean minus one standard deviation. One standard deviation above, mean plus one standard deviation. Between a z-score of 1 and -1, we have an interval. And this interval is what we would call within one standard deviation. Now, how do we get this 68%? Well, the long answer would involve a description of something called a definite integral, which is a theme of calculus, okay? But simply put, in statistics, the area under a distribution curve is the probability of something happening, and that's going to be a repeated theme throughout the year. So this 68% refers to literally the area between the curve and the x-axis bounded by this interval from -1 to 1, z-score, okay? It's literally an area that denotes the probability of something happening. That something being a random variable assumes a value within one standard deviation of the mean. Let's expand our horizons a little bit. We're now working within 2 standard deviations of the mean. 95% of our data are within 2 standard deviations of the mean. Again, we see z-scores of -2 and +2. Mean minus 2 standard deviations, mean plus 2 standard deviations. And over this interval, we have 95% of our data approximately. Note these approximate signs, by the way. We're not making guarantees. Very seldom can you do that in statistics. You could argue that's why we have statistics at all. About 99.7% within 3 standard deviations of the mean. So we have from a z-score of -3 up to +3, mean minus 3 standard deviations, mean plus 3 standard deviations. This area under this normal model, if you're talking z-scores, standard normal model, that's going to be 99.7%, nearly 100%. Almost all data are going to be found within 3 standard deviations of the mean. And it is not uncommon for you to have a set of data in which none of the values are outside of 3 standard deviations. Is it possible? Yeah, that's not 100%. But it's highly unlikely. Only 3 out of 1,000 would fall outside of 3 standard deviations. Here is a further breakdown of the normal model. We can use symmetry to say that this middle 68% can be broken up into 34s. Then these 2 blocks right here denote 13.5% on either side. By the time we're out at 2 standard deviations from the mean, we have 95% of our data, so these 4 values should and do add up to 95%. Then we have 2.35% approximately. Again, these are all approximations. These little extremities here are going between 2 and 3 standard deviations on either side. And then 0.15% on either side of the past 3 standard deviation zone, totaling to 0.3%, 3 in 1,000 beyond 3 standard deviations. The sooner you can put this graph to memory, the better this year is going to go for you. So I challenge you, put this graph to memory. It will be a great resource to you. Okay, so let's use the empirical rule. Let's use this 68, 95, 99.7 rule. A study of men's health measured 14 body characteristics of 250 men. There's our sample. One of which was wrist circumference in centimeters. The mean wrist circumference was 18.22 centimeters, and the standard deviation was 0.91 centimeters. A histogram of all 250 values looks like this. And let me tell you, that is a histogram that is begging to be analyzed with the 68, 95, 99.7 rule. So will that rule provide useful percentages from these data? Absolutely. The nearly normal assumption is more than satisfied. About how many of these men does the rule predict to have a wrist circumference larger than 20.04 centimeters? Okay, so how would we solve this problem? We would first note that 20.04 centimeters is exactly 2 standard deviations above 18.22 centimeters. Now, how do I know that? Well, a standard deviation is 0.91 centimeters. If I were to double this and add it on to 18.22, I would get 20.04. So 20.04 is above 2 standard deviations. Okay, so now I'm going to use my breakdown of the normal distribution to get my answer. So, as I've said, 20.04 centimeters is 2 standard deviations above the mean. So I predict about, okay, well here's 1 standard deviation, 2 standard deviations. We have 2.35 plus 0.15%, that adds up to 2.5% of the men, or about 6 men, 2.5% of 250 is 6.25, we'll round that to 6, will have a wrist circumference greater than 18.22 centimeters, okay? So I used my normal model, found a percentage, and then solved the problem which asked how many of the men. So I need to list a number of men, take this percent, multiply by the size of the sample, and I get my proportion of the sample that I predict, not know, predict, will have a wrist circumference larger than 20.04 centimeters. Here's another problem broken up into 2 parts. Suppose it takes you, yes you, 20 minutes on average to drive to school, with a standard deviation of a mere 2 minutes. Suppose a normal model is appropriate for the distributions of driving times, okay? Well, I'm glad we can assume a normal model because I have no idea how we do this problem without one. So, how often should you arrive at school in less than 22 minutes? How often can we expect or guess that we're going to arrive at the school in less than 22 minutes? All right, estimate would be the best word. How often can we estimate that? And then second, how often should it take you more than 24 minutes? How often is it going to take an especially long time to get to school? Might be something nice to know. All right, so feel free to try these 2 problems on your own using the breakdown of the normal model. And as an added bonus, try to do this without staring at the normal model the whole time. See if you've already put it to memory. If not, that's okay. You got plenty of time. So pause the video, try this one, and then unpause the video when you are ready to look at the answers. Okay, I'll assume we're ready to look at the answers. Here we go. Part A, 22 minutes is 1 standard deviation above the mean. Yep, 20 plus 2 is 22. Easiest problem of the day. Mean is 20, standard deviation is 2, bada bing, bada boom. So I predict that you'll arrive at school in under 22 minutes 84% of the time, right? How'd I get that 84? Well, 1 standard deviation above the mean is marked off here. The left-hand side of the bell curve has 50% of the data. You can add these up. Or you can just acknowledge that this curve has bilateral symmetry relative to the mean. So 50% on the left and 50% on the right. That's a useful tip to know. So if we're talking under 22 minutes, 1 standard deviation to the right of the mean would include all of this area over here, which would be 50% plus 34 is 84%. Right? So we're 84% likely to arrive in under 22 minutes. Also, 24 minutes is 2 standard deviations above the mean. So I predict that you'll arrive in over 24 minutes about 2.5% of the time. This is identical to the problem we did on the prior slide. 2.35 plus 0.15 is 2.5. That's above 2 standard deviations, so that is the odds that we would arrive past 24 minutes. All right, last one here. Beginning in 2017, public companies will be required to disclose the ratio of CEO pay to median worker pay. This book was written in the late 2010s. The Glassdoor Economic Research blog has published the data for 2014. Here are some of those data. The total compensations in millions of CEOs of $441 top public companies, right? So here is we're talking about money and it's wealthy people. So this is going to be a right skew curve for sure. So to that point, will the 68, 95, 99.7 rule provide useful percentages from these data? All right, explain briefly. Using the rule about how many CEOs should have compensations within one standard deviation of the mean between 2.54 million and 25.26 million, we are just given those values. That is within one standard deviation of the mean. So first we're going to use the 68, 95, 99.7 rule. Okay? What does this rule say? How many CEOs should have compensations within one standard deviation? Well, 68%. That's what the rule says. Within one standard deviation, we can expect 68% of the data. But within one standard deviation of the mean is between 2.54 and 25.26. Let's estimate the number of CEOs within one standard deviation using the graph. Well, 2.54 is somewhere down here near 0, and 25.26 is somewhere around here, so basically all the data, except these high values over here. But we should not expect to see all of the data with one standard deviation. We should expect to see 68% of the data within one standard deviation according to this rule. What gives? Well, what gives is that you shouldn't use this rule, okay? Notice this is a right skew curve. Can we assume that this is nearly normal? No, we cannot assume this is nearly normal. It is not normal at all. It is very skewed to the right, all right? We got our corgi tail to the left and our, I don't know, we were talking about dinosaurs early in this lesson, so this dinosaur tail out to the right, okay? This Apatosaurus tail out to the right, okay? That's not going to work, okay? So this is a good example because it lets us know the 68, 95, 99.7 rule is a neat rule as long as this is a bell curve. And this does not constitute data that a bell curve describes, right? So we got to be careful.